All right, gang, Math 1500 again, linear regression. This is a follow-up from correlation, the correlation video. So let's assume that we've examined the relationship between some x and some y. And guys, it's important that you understand that both x and y are quantitative variables. So for example, if you're looking at the relationship between gender and ACT score, well, ACT is quantitative, gender is not. So if you're looking at the relationship between gender and ACT, there is a statistical procedure out there, but this is not it. This is I don't know why I'm writing so, like a, whatever. Okay, so this is a procedure, statistical procedure technique that we use to examine the relationship between two quantitative variables. That's a restriction. If I want to look at the relationship between gender and beliefs about abortion, pro-choice, pro-life, then I have two categorical variables. There is a statistical procedure that you can use to examine that relationship. This is not it. This relationship, again, is to examine the relationship. I'm sorry, this technique is to examine the relationship between two quantitative variables. So we're assuming here we've examined the relationship between x and y using what? Scatter plot, R, and R squared. Let's assume that our R was statistically significant. Okay, if all this is happened, then we would want to get into a technique called linear regression. And guys, linear regression just further explores, it describes the relationship between x and y, but it also creates a mathematical model that we can use to predict y values for future values of x. So let's run through just a general example, okay? We'd like to explore the relationship between some x and y. First thing we want to do is we look at a picture. And we look at the scatter plot, and we determine that this thing is linear. It's negative, and it's strong. The second thing we would want to do is we'd want to use our calculator, or we could use R. Use R to find R. That's kind of weird. Use capital R to find little r. So use the statistical software package R to find the correlation coefficient. Well, let's say we did that. And let's say that R turned out to be negative 0.83. So R squared, let me grab my calculator here. Would be 0.6889. Or 68.89%. Furthermore, let's say that we found out that R is statistically significant. then it would be appropriate to come to our scatter plot, come to the relationship between x and y, come to our ordered pairs, and create a mathematical model, in this case a linear model, that best fits our data. Now this is going to give us some components that are going to allow us to better explain the relationship between x and y. It's also going to give us a mathematical model whereby we could use that model to predict the y value for future x values. Okay. Now, how do we choose this model? Well, I'm not going to get into it too much, but I'm going to give you just it's way too advanced for this class. But what it does is, if we think about just having just a very simple model here, we want to get what's called the line of best fit. And what the line of best fit will do, it'll take the distances from from each point to the line, and it kind of sums them up. It squares them for a reason I won't get into here. But it wants to find the line that has the minimum sum of the distances. Now, we call those sum of the deviations squared in big fancy schmancy statistics classes. But in this class, I want you to think about just the sum of the distances squared, or the sum of the distances. Now, what about that line right there? Well, these distances from each of those, if I sum those up, that's going to be a pretty big number, right? I mean, it's not a matter really of the magnitude of being big or small. It's just, could we get one better? Well, that one looks better, doesn't it? And that one looks better. Well, guys, there's some line called the line of best fit that if I look at the distances from each point, the sum of the distances from each point to that line, I can find one that minimizes these distances. So this is called minimizing the sum of squares. And again, if you want to learn more about that, come talk to me and we'll do an independent study or something. But so again, our goal is to find the line of best fit for prediction. Now, this brings in a little bit new notation. Y is just the observed y value. X stands for the observed x value. In a previous example, I said that we may have someone that scored an 82 on a midterm and a 92 on the final if we wanted to examine the relationship between a student's midterm and their final, and we take an entire class. Well, our x here is the 82, and our y is the observed y value. But our model is used for prediction. So when we put our x values into our model, we won't necessarily get the y value that that we observe from the person. Because of that, we change the y value in the equation to what we call y hat. And y hat is just the predicted value of y for an x value. So for example, up here, well, I think this is probably better illustrated through an example. Let me go through some real life data and show you some ordered pairs. We'll create this line, this best estimate, this line of best fit. It's called the least squares regression model. And then I'll calculate a y-hat for you and show you how the y-hat, what we predict, doesn't necessarily align with what we observed. And we give it a name. We call it a residual. All right. So I think what's best is let's just go in. I got some data here. Let's look at a problem and work it. So the table below gives horsepower and miles per gallon for 15 randomly selected vehicles. Using the data, consider the equation of the regression line. So that's what we call this thing. Y hat equal B0 plus B1 times X. Guys, B0 is our intercept. B1 is our slope. So we have a standard linear model, but this linear model is being fitted to a relationship that's linear, and it's being used to predict values of y for particular values of x. Okay? Now, so we want to be able to do this, use this model to predict miles per gallon for a vehicle based on its horsepower. So we're going to go through this mathematical technique here, this statistical technique, if you will, where we're going to create this model. So if we have a future car that comes in with a particular miles per gallon, if we have a vehicle that comes in with a particular horsepower, we can predict its miles per gallon based on its horsepower. Now, I tell you, keep in mind that in practice, it would not be appropriate to use the regression line to make a prediction if the correlation coefficient is not statistically significant. It would be appropriate to create the model to better explain the relationship. But once we get into predictions, we want to assure that we have a statistically significant model based on the statistical significance of the correlation coefficient. So let's see how this plays out, okay? Now, first thing I ask you to do is to find r and r squared, and hopefully I've impressed upon you by now that the best way to do that is to use your calculator. So guys, I've already gone ahead, so I'll go stat, edit. I've already gone ahead and typed these in just to save time. Okay, so very carefully while you're typing these, I'm just going to go through and make sure I've got no typos. And you'll probably not get yours typed in as quick as I do my, because I want to make sure that I've got the right numbers, and I want you to make sure that you have the right numbers, because it's really frustrating for students if they're doing everything correctly, but they're getting different numbers than me. Just because they have a typo. So just pay attention. Just check, double check, and it works out much better if we don't have typos. So guys, I want to go second function quit, and then I will go into stat, and just like before, I want to go over to test, and I want to go to linear regression t-test. So I've got my data. X is in L1, I got my Y's in L2. Remember from last time I had you put Y1 in regression equation, so you should have that there. Showed you how to do that in the previous video. And I hit calculate. And I scroll all the way to the bottom. And I see that my R value is negative 0.87. And my R squared is 0.75. So I'm showing a strong negative relationship between horsepower and miles per gallon, which says cars with more horsepower have lower miles per gallon. it makes sense if you think about a Hummer, which has a tremendous amount of power. You're not expecting to, if you're reasonable, you're not expecting to get a lot of miles per gallon out of a vehicle like that. Now, I don't ask you to do that this in the handout, but I want to go ahead and get a picture. It's really easy to do. Turn it on. Select the first picture you see there. That's the icon for a scatter plot. Make sure you have L1 and L2. Remember, if you hit zoom 9 here, you're going to get some problems. So let's scroll back up to the top and then hit zoom 9. And you can see that you have your scatter plot, which clearly shows a negative linear relationship, and I think a strong relationship. But you're seeing the line of best fit, the regression model, because of that Y1 that I instructed you to put in right here. Down here where it says REGEQ, that Y1, that's the reason you're seeing the line. If you didn't watch the previous video, you're not getting the line, so I'm not going to show you how to do that because you can go back and watch the video. But anyway, guys, the purpose of this video is to learn more about this line. To learn more about the line. Okay, but we got a couple of steps before we get there. Okay, so is R statistically significant? Well, you know, we're going to do the same thing we've done before. We're going to test, these problems are always, we're testing rho equal to 0, rho not equal to 0. We're going to create our test statistic. Well, next thing we're going to do is we're going to set our alpha, and it's not given, so it's going to be always at 0.05. If it's given, use the value it's given, but if not, we'll use 0.05. You know, really, it probably would have been better to go out a little further on the R. Let me bring up the calculator here and go out a little further on that R. We're just going to get a better. Okay, so R negative 0.8687. I'm going to do that. I'm going to go out 4 places. So negative 0.8687, right? Yeah, I'm going to use that. I don't use my R squared. Actually, I do use my R squared, so let's go out 4 places on it too. 4, 6. All right, gang, we know that all I've done is I've just went out a little further. Now, we know that the test statistic for this problem is R over the square root of 1 minus R squared over n minus 2. So, essentially, we have negative 0.8687 over the square root of 1 minus 0.7546 over n minus 2, so that's going to be 13. Now I'm going to show you the way I would do this. I don't necessarily like to put this all in one command, but you can. I mean, it's easy to do. In fact, I'll do it this time just to shake things up a little bit. I'll tell you something kind of cool. I forgot all about this. If you go to variables and come down to number 5 and go statistics, you're going to have the information that we got in this problem, I think. Well, actually, you don't have it after all. Yeah, you do. So we could go R divided by the square root of 1 minus. So let's go back. I think this was number 8. Divided by 13. Now this is going to take no, it's not going to round R at all to 4 places or whatever. It's just going to use the entire thing, so the entire number. So when I do that, I get negative 6.32. Now, if you're sitting there thinking, all right, that's cool, that's fine, but that's just a little bit too much for my brain to handle, then let's do it the way I did before, okay? So I could, first of all, I could go 1 minus 0.7546. I can divide that by 13. I can take the square root of that. And I can take my negative 0.8687 divided by the answer. And you're going to see we're going to get something very, very, very close to the answer we got otherwise. It's going to be off a little bit out further, but to 2 digits, it's going to be the same answer. All right, gang, next thing we got to do is we got to figure out our p-value. So remember, our p-value is going to be in the distribution. It'll be from negative 6.32 and down, from 6.32 and up. So degrees of freedom here is going to be 13. Because we have 15 degrees of freedom, we have to account for 2 estimations here, an estimation of x and of y. So let's do it. So I'm going to do the upper tail. So that's 6.32. Up to E99. 2 degrees of freedom are 13. I need to multiply that by 2 because they have 2 tails. So my p-value equals 0.00027. So boys and girls, we have statistical significance. So it makes sense now to create our linear model, not only for to better explain the relationship between horsepower and miles per gallon, but to also use our model for prediction. All right, so next thing we get into is we get into the information about our model. So guys, remember that a statistical model like this was probably presented to you way back when is y equals mx plus b. And you were told that the m was the slope and the b was the y-intercept. Same thing. We're going to do the same thing here. The value that goes with the x is the slope. So guys, b1 equals the estimate of the slope. And b0 is the estimate of the intercept. Now, you're probably thinking, now what's up with this estimate thing? What are we talking about an estimate? We're going to get the slope. Why is it estimating anything? Well, guys, if you go back to the problem, it says that we have randomly selected vehicles. So what we're trying to do here is we're trying to take the information from these 15 vehicles and generalize to all vehicles. That's what we did down here. This correlation coefficient, negative 0.86, that's specific to these 15 vehicles. But we could have randomly selected 15 more vehicles, and we got something different. But by generalizing and conducting this test of hypothesis, we can conclude that we would reject the null hypothesis and conclude that the correlation coefficient is not equal to 0. And we could actually get into a, just like we do for hypothesis testing for mean, we could follow it up with a confidence interval and get within a 0.95 probability the value of that. I'm going to do that. Get on a little bit of tangent here. I'm not going to require you to do this, but I'm going to show you how it's done. So guys, if I come over here and if I go into linear regression t interval, I can set my confidence level just like we've done previously. And it's going to give me a, wait a minute. Apparently, okay, my bad. It doesn't give a confidence interval for the correlation coefficient. It gives a the confidence interval for the slope only. So, guys, forget that. Sorry about that. But anyway, find the estimated slope. So what we've got to think about here is we're going to come up with the model for our 15 cars. And this is ultimately used to estimate the model for all cars. Now, just like using X bar to estimate mu, the X bars will range from, will vary from sample to sample. These beta 1s will vary from sample to sample. We just got one of them, okay? And it turns out that it's super, super, super easy to find when you learn how to use your calculator. So, guys, let's do that. Using our calculator, we've got our information. And it turned out that when we did our stuff before, when the linear regression t-test, that we had all the answers to our problem on that one particular screen. Guys, if you look at the top, you'll see you have y equals a plus bx. A is our b0, b is our b1. Because b is the number that goes with the x, so it's the slope, and a is the number that goes without the x, so it's the intercept. And these values are given right here. So guys, from our calculator, we can see that the a value equals 46.87. And the b value is equal to negative 0.084. So guys, going back over here, this information tells me that my model is this. So the negative 0.084 is the estimate for the slope. And the 46.87 is the estimate for the intercept. Guys, it's that easy. And if you get on a test and you start flipping out and you can't remember which one is which, all you have to do is look up here at the top. Y equals A plus BX. You just have to remember that the number that goes with the X is the slope, and it's given right here. The number that goes without the X is the intercept, and the A, 46.87, represents that number. So, in a nutshell, guys, go back over to this. We can predict miles per gallon. Anytime in statistics we put that caret above something, that's just the predicted value. We can predict that by taking 46.87 minus I forget what it was now, 0.084. Yeah. Times the horsepower. So gang, for a horsepower of 300, we're going to predict the miles per gallon to be 21.67. So we're predicting about a car that gets about 22 miles per gallon. Now, your calculator is what's called order of operations smart. It'll figure it out. It may be better to think of this as your calculator is going to do, again, it's called order of operations smart. So, back to our handout here. Estimate the mean miles per gallon for a vehicle with horsepower 205. Well, we saw when the horsepower was equal to 300 that the miles per gallon was 21.67. Yeah. And you can just plug and chug there. You can just insert the number in for X and solve it, the way that we did. But there's also a function on your calculator that does this for us that I want to illustrate. If I can find the calculator, oh, there it is. Now, if you go back to graph and you've got your line on your scatter plot. Now, it won't make a prediction if the line's not there. And the line is not going to be there unless you put that Y1 by the REGEQ that I taught you how to do in the previous video. There's one way that you can put the value in your calculator and get it very quickly. So if I go second function calc and go to value and just type in the 205, it will give me my predicted value. Right down here at the bottom, it'll have Y equals 29.69. And up at the top, you can see this 46.87, and it keeps the string of digits there, I don't know, out, 10 or 12. And then you can see the minus 0.083, it's getting ready to get into the rest of the slope and so on and so forth. So it uses more digits to calculate, so it's going to get a better answer. I'll show you how it's off maybe just a little bit. When we did 300, we got 21.67, and they get 21.73, so it's off a little bit. Their answer's better. Again, they used a further decimal expansion on their slope and intercept than what we did. We only went, or what I did, I only went 2 places. Actually, 3 places on the slope. All right, so either way you do this, it's okay. But again, you can't make a calculation if your regression equation isn't there. So let me go in Y1 and get rid of that. And now let me go to graph. All right, there's my scatter plot, but I don't have any line there. So I go up here and go second function calc and go value 300. And it's like, what are you talking about? There's nothing there. I got nothing there. So I try to put 300 in, it won't let me because I don't have anything in the Y1. Okay, so the line of best fit, the straight line, the regression model, hasn't been drawn, so I can't make a prediction. Final thing here is, my bad, that's from some time ago. Final problem is interpret the slope. Now, you guys remember learning linear models way back when? Probably some of you learned it in 7th grade, some 8th, some 9th. Maybe you didn't even learn it to college, and if that's the case, that's fine. But I guarantee you've seen y equals mx plus b taught in detail. In fact, it's a prerequisite for this class. Well, if you were taught really well, your professor probably, professor, teacher, whatever it may have been, probably gave you some simple linear equation and told you that the slope is 3 and the intercept is 1. And they probably had you draw one of these one of these very, very meaningful and useful tables where you put in a couple of numbers and you calculate the value for y based on the x. So if I have x equals 0 and I put it in for x, my y value is 1. If I put 1 in, I get 3 plus 1 is 4. If I put 2 in, I get 6 plus 1 is 7. And if I put 3 in, I get 10. Now, if you were taught well, your teacher should have pointed out to you that as you increase 1 unit over here on the x, that your y values change at a constant rate. And that constant rate is exactly the value of the slope. Now, if you were taught well, your high school, college, whatever it may be, teacher, instructor, professor, whatever it may have been, should have also shown you that the y value for this line will always be the y value you get as the y-intercept, because it is exactly the definition of the y-intercept. It's the value of y when x is equal to 0. That's the interpretation, the definition of a y-intercept. But what's the definition of a slope? Well, if you were taught well, it's right here. As x increases 1 unit, the y value increases the value of the slope. In this case, it's 3. Now, how can we use that to our advantage to come up with an interpretation of the slope for this problem? Same thing. As x, which in this case is our horsepower, increases 1 unit, just like we did over there in our chart. Our y value, but in this case, our y value is what? a predicted y. Our slope is negative here. Decreases. .084 units. Guys, this illustration over here that I used using this table, if I had used this what happens? I put 0 in, I get 8. I put 1 in, I get 6. I put 2 in, I get 4. I put 3 in, I get 2. As I increase 1 unit, I decrease the y exactly the value of the slope. So that's what happens in our regression model. We predict, using our model, that for each unit increase in horsepower, our predicted y, because that's again what our y value is up here, decreases 0.084. All right, gang, that's it for this video.